So without no further ado, I would like to commence my tutorial. The first question I would like to ask everyone is, has anyone witnessed flooding before?
Has anyone witnessed flooding before? Yes, we are seeing a few hands going up, maybe 10 or 15 people.
Nice. Do you ever wonder what could have resulted into flooding? Probably the river bank overflowing, or probably a lake overflowing, or probably a dam overflowing. So that's because there has been serious changes in the volume of data, in the volume of water that is currently in either the lake, the reservoir, or the river. And important parameters that we need to be able to monitor this and predict it is the change in water level elevation, which is the height. Now, considering that in the past, we've had the use of gauge data that are limited by their sparse distribution and inability to locate them in remote areas. The use of remote sensing has been quite successful in this area. And over the time, we've had like different satellite altimetries that has helped us in monitoring water elevation, which is then being used to calculate the change in volume as well as the quantity, or let's say the quantity of water that we have in a particular lake or a dam, or it could also be like a river. Now we have ICESat-2, and I'm sure you guys have gone through like the introductory part of ICESat-2, the different products that we have in ICESat-2. And this particular product is the ATL13 product that is specifically made for hydrology. So if you guys have worked with other products, which is, for example, the ATL6 or probably the ATL10, 11, and others for different purposes. But the ATL13 is basically for inland water monitoring. And this is because there has not been like any satellite that has been specific for inland water monitoring, except the just launched SWOT altimetry satellites. So now in this tutorial, I'll be showing you how you can monitor change in water surface elevation. And by the end of the major objective of this tutorial is to understand ICESat-2 ATL13 product and its usage for inland hydrology, which is more like the water monitoring. Then the ability to access and extract the required subset variables in the ATL13 products. And then at the end of the day, I will expect you to be able to create a water surface elevation dynamics over time for different sites. It depends on your location or your study area. So as I've said in my introduction about altimetry satellites, basically altimetry satellites operates by monitoring the time it takes the pulse to reflect from the object back to the satellite. So it monitors the time. So it is now this time that is converted into the height of whatever you are monitoring. It could be water, it could be building, or anything you are monitoring. So, but for now, we are monitoring water heights. And yeah, this is more like the popular formula, which is the altitude, the range, then some of the atmospheric and corrections that you need to do to get your altimetry height. Yeah, this is more like the historical background for altimetry satellites. So here I'm talking about different resolutions and ICESat. So in the past we've had ICESat and now we're having ICESat-2. So ICESat-2 is currently the satellite that has a better footprint resolution, which is about 17 meters approximately. So now you can also get some information from this particular document about all of the different variables that we have in the HCl13 products. So now I would like to ask if you have any questions before we proceed more to the technical parts aside from this introduction. Do we have anyone that needs any clarification?
Doesn't look like, yeah, it doesn't look like any questions, Shamsuddin. It looks like we're good to go.
Okay. So I'm sure you guys must have done like the introductory part of IcePeaks. So in this particular tutorial, I'm using IcePeaks to download my required data. And the location I'm looking at is Lake Victoria in Central Africa. So the first thing you want to do is to make sure, you import your IcePeaks and then more like a print command just to print your output. So, and before that, you must have actually installed the package. So now after that, knowing fully well your study area and the place you are interested in, which is Lake Victoria, you need to pick in the coordinates of that particular location. So by picking the coordinate or defining the boundary area, you start with your lower left longitude and the latitude, which is, let's say I'm interested in this is the Lake Victoria. So you start with the coordinates, which is the longitude and latitude of this particular point, which is the lower left. And then you proceed with the longitude and latitude of the upper right, which is this part. So those are the informations that you put into this part. And again, you want to know what time are you interested in. So it depends on the kind of study you're doing. So some people might be interested in a longer period, while some might just be interested in, okay, let me see what height the water is before a flooding event occurred and after a flooding event occurred. So you need to impute your dates. So for this, we are doing since 2018, which is October 1st, 2018, up to July 2023. And we are looking at this time. So we have a start time and our end time. So after imputing all of this, we have so this command will tell you the number of available granules that you have for that particular area. So this will also tell you like, oh, the required storage that you need for that particular area. So after filling in all of that and running that, then you need to log into your Earth data. You need to put in your Earth data login information. So basically you need your username and your email. So after that, it will tell you user authenticated, and then you can proceed. So in this part, it's more like you downloading the old data. So this will download all of your data for you. And yeah, it depends on your storage. So I have my data downloaded into the storage parts. So after all of that, then you have your data for your analysis. So after this point now, we can now proceed into more like the technical analysis, extracting the data that you need for your analysis. So before going forward, do you have any question before now?
Looks like no questions.
Okay, so if there's no any question, I would like to ask, is there anyone that is currently working on water surface monitoring?
Who is working on water surface monitoring? Anyone? Yeah, we've got one person here, Shamsuddin,
Okay,
and a
so
couple more.
okay, so can that person just tell me, like, okay, if you, let's say you are interested in monitoring the volume of water in that place, do you think you can use ICESat-2 based on the brief introduction that we did and this particular step that we just did?
So do we think we can use ICESat-2 data to look at the water surface heights or volume? Is that what you're asking, Shamsuddin?
Yes.
Yeah, any insights on that from our community here? Tell us more, Shamsuddin. Do you mean based on what you've shared with us so far?
Based on what I've shared so far, like, does anyone feel comfortable saying, oh, based on this, I want to use ICESat-2, and can you download the ICESat-2 data on your own without using all of these codes?
Yeah, what do you folks think? Yeah, we're getting some nodding heads. My guess would be that we've got some skill in downloading the data, but I think we're interested in, or maybe still learning a bit about how to use that for this particular application. Yeah, that's what I'm thinking. Okay.
So now moving forward, we have our, so now moving forward, since we have all our data already saved, and I can share how the data looks like, so you can see, oh, when I download my data, how does it look like? So this is how your data look like, and it's saved in .hdf file, and it is now that HDF file that you now extract the required variables from. So now, moving forward, the first thing I want to do is to import all of these packages and make sure you have all of them imported, like the H5PY, which is mainly used for the extracting of data from .h5 and .h5 file. Then your NumPy, your OS, RE, Globe, your pandas, then multiple processing. Also, you have another package that you need to also convert your dates from the GPS time to the Julian time, dates, and year. So after importing all of this, you need to define where you have your data saved. So here is my own working directory. And then the first thing I would like to do is to list my files. So using the globe package, the globe function, then I can list all files that starts with processed_ATL13 and ends with H5. So if I have any data in this format in my folder, then it will tell me. Now in ICESat, we can remember that we have like 6 different bins, which is the GTL1, one. The one has two beams, which is the left and the right, which is also the weak and the strong one. Then the 2 also have left, right. Then the 3 also have left, right. So you want to specify all of this. And in case, let's say your water body is so big that you're only interested in maybe the GLT2, So you can also choose, probably you're interested in just only one of the ground track. So yeah, you can also specify that. But for this particular exercise, the reason why we are doing this is because, yeah, we assume that we're not assuming that we can see like our lake is not very, very big, like it's not more like a very large lake. So that we can have like a lot of observations, then we decide to use all of the ground tracks. After that, you want to now loop into each of these ground tracks, okay, and then extract the required or the variables that you are interested in. So this ICESat-2 HCl3 product provides us with the longitude, the latitude, the height, which is autometric height, and it also provides us with the ellipsoid height. So there is difference between autometric height and ellipsoid height, which is one with WGS 84, and the other one is the one EMG 2008. So you want to also get the time. Then we have some quality flags variables. So these are the variables that you can use to remove like probably bad shots from your data, just to have a quality product at the end of the day. So for example, we have the QF background, we have the QF bias, we have the bias fit, we have the significant wave heights. Let's say you're working on a more larger lake, and then considering the change in the wave height, then you might want to correct that. So after specifying all of this with your for loop and your if statements, then you can specify the all of the variables. So if you have all of this in my X, which is my ground track, then extract all of these variables for me. So in this, I have created a data frame. So this will be stored in a data frame. And at the end of the day, you can export this data frame into a CSV file. So with this CSV file, you can either use it in ArcMap, QGIS, and any other software that you want to use it in. So now, after that, I will specify all of the variables, and then it will be labeled in this way. And then I will also add another variable, which is subgroup. So what this subgroup does for me is that it will be able to identify where each of my shots is coming from. Is it coming from the GTL, the 1, 2, is it from right, is it from left? So it's going to do all of that for us. Now, at the end of the day, it will concatenate them, it will match everything together, and then produce like a data frame for us. So you can choose to export your data frame into a CSV file. Now, before moving forward, I would like to know if you have any question for this particular part. Because this serves as the major part after downloading your data. So this is the part that you want to specify the kind of variables that you need. And in case you actually miss any variable here, that means you need to still redo it again. And so you want to get all of this right before you proceed further.
Any questions so far? We'll check in here. We have one question coming your way.
I wonder if iSpeaks or one of those packages have like a way to read all these variables, and you don't have to like go and manipulate the dictionary, like, or it's something specific that you need that from different variables that maybe iSpeak doesn't load from the file?
Yeah, that's a very good question. So basically, you can from your iSpeaks, if you look at more like the document for iSpeaks, yes, you can specify the variables that you want. So you can specify, let's say you are interested in just maybe 5 variables, you can specify from iSpeaks. But still, when you download all of the data, it will be in .h5. And at the end, you still want to extract that variable into more like, say, a CSV file. So yes, you can specify those variables, but you still need to extract all of them at the end of the day into a better format that you can work with. Let's say you can use it with other GIS softwares. Does that answer your question?
Yes. Any other questions? All right. Looks like we're ready to continue, Shamsuddin.
Yep. So now I'm pretending I have ended this particular section and now in a new section. So the section I am now is that I have exported my CSV file. Now I'm importing the CSV file back into my Jupyter Notebook. So now I've imported it, then I want to rename it. I can give it, you can decide to rename it or you can decide to leave it. So I like to rename my variables after importing it. Now, one thing you want to be sure of is that your particular product that you've downloaded or the data that you'll be analyzing at the end of the day does not contaminate with ground. Because, so what that could result into is that you are monitoring the elevation for land and water at the same time. And you don't want to do that. So you just want to monitor the one for water only. So as you can see this now, you can see that the shots goes beyond the water. So if I just analyze the data directly, then that means I'm doing something wrong in the sense that it's already monitoring out of my water body. So what you want to do in this sense is that you want to import, probably you have a shape file or a KML file that you want to import just to make sure that the data you are analyzing falls just within your water body and it's not contaminated with land. So with that, I use the GPD function to bring in my shapefile, which is for Lake Victoria. So another thing you don't want to do is that you don't want to monitor the whole of the whole extent, because yeah, you still need to put in like some buffer zones for you to be able to get a precise and more accurate water surface elevation. So now I have a function whereby when I import my shapefile, it will extract only data that falls within, like that falls within that particular shapefile. So you can use this code. So at the end, I name it filter by polygon. So now at the end, I am able to extract the required data, and then I have it as my CSV data frame now. Now, one thing you want to be, I'm sure you guys must have done this, like converting from the GPS time to our normal Julian, the one we can relate with, which is the day, the time, and the year. So I have a particular function from this particular. So here is in case you have like an external function that you have saved on your working folder and you want to import it. So you can just use the run, then -i convert, then you can So this is the name of the folder that, I mean, the function. So you can just import it. Now, here are the conversion process that I went through. So the first one is to convert it into, to have a year, to have a month, and then to have a day, hour, minutes, and also seconds. So in the end, I have all of that converting my time. So this is my original time from the ICESat-2. And at the end of the day, I have it converted to, I have year, month, and day. So at the end of the day, I can also have like a time that will show everything all together. So now I want to drop like the day, the year, month, and dates, because yeah, it's not useful to me again. I already have like a particular time that I can always use. So now you have your data, and the next thing you want to do is make sure your data is of high quality. And one of the things that we'll do is to remove outliers from each of the data. So outliers could be, let's say, it could be as a result of cloud cover, or it could be as a result of the time that it's been shot, or it could be as a result of other atmospheric or geometric issue. So you want to remove where you have outliers, maybe more than the mean or very lower than the mean. So here I'm using a particular method, which is interquartile range. So what this interquartile range does is that it removes outliers that falls within the upper layer and then the lower layer of the interquartile. So me removing that, I have a function already. I can import that function and then run this code. So it will remove the outliers for me. So in the end, I have a clean data now. So now with this data, I can now work with it to do my water surface elevation time series. Now, the next step is, okay, you've gotten different shots for just a particular day. So as we know, like we can get more than 100 or more than 100 shots per observation. So what you need to do now is that you look for the average. So the average of each day's shots is what you then look for. So there are some studies that have adopted the median. So those studies adopted the median just because the lake or the water body is very large, and the slope of that area it's very obvious or very, very high. So you want to adopt the median in that case. But let's say you just have like a smaller lake, and then you want to do the times, then you can easily adopt the mean. Another thing that we do is the standard deviation. So in this sense, we are looking at, let's say, looking at the area of this lake, and we have a shot for this particular day, for just one day to be around this part. Reasonably, the spatial distribution of that particular shot is not even. So you want to produce like an uncertainty for what you are doing. Let's say you want to say, okay, now I've done this, but there is uncertainty in the spatial distribution. So existing studies that I know have adopted the use of standard deviation for the spatial uncertainty. So that is for the spatial uncertainty. It's large, and then it can cover the whole place. So for this particular day, we'll calculate the mean and then the standard deviation. So the mean value is what we adopt as our water surface elevation or water height for that particular day. And then the standard deviation is what we adopt as our uncertainty. So after doing all of that, then the next part is to plot your time series. So with these plots, the first thing I do is to make sure my dates are sorted. So it's sorted so that I won't just be having, oh, my scatter plot here and there. Then I have to sort it first. And then plot the mean, which is my water level or water surface elevation. So now we can see that from 2018 up to July 2023, the water level has changed a bit, majorly in 2020, probably due to increase in precipitation during that period, or it could be maybe lesser temperature or other climatic variables. And yeah, it shows that there has been a rise in the water surface elevation over time. So now another thing you want to do is to plot the uncertainty together with, so that anyone that is using or anyone that is reading what you've produced will be able to know, okay, this particular measurement is based on this particular uncertainty, or is based on this value of uncertainty for a particular date. So far, we've had about, the highest uncertainty that we had was 0.25 meters. And that was at this point, yeah, where we have the highest. So you'll be sure of, say, okay, in case you want to use this data in another model, let's say some environmental physical model, then you can say, okay, for this part, you can know the uncertainty of your data. And that because so you can say, because in the end, the level of uncertainty of the data you are putting into any of your model will determine the accuracy. So here we plot the uncertainty and the water volume elevation. Now, another thing you might be interested in knowing is that, okay, at what rate is this water elevation changing over time? So with that, you can fit a linear regression across your water surface elevation and graph, and that will produce like the rates of change for you. So now from this equation, it shows like the water surface has changed probably on a daily basis at 0.0095 between 2018 up to 2023. So I want to thank you for listening and following all through to the end. I hope this was interesting and educating to you. In case you need further readings, then you can also go through the references and do some further readings to know how it's been done. And yeah, if you have any question, I'm much happy to take your question. Thank you.
Let's thank Shamsuddin. Really interesting work, Shamsuddin. Thank you. We'll just check in if there are any questions.
Hey, thanks for that tutorial. I was curious, you saved a bunch of or put some quality flags into the data frame, and I was wondering if you could talk more about how you might use that also in thinking about this data and the results.
Yeah, thank you. So now looking at some of these quality flags. So we have the QF bias. So from the So when you look at the full documentary for the technical documentary for ATL13, so there are, let's say, acceptable value for each of those variables. So you can follow each of, so it depends on whatever you're doing. So it's not like it's constant, but there are acceptable value for each of those flagging parameters. So when you look at this particular document, then you can be able to figure out, okay, which one do I want to use in all of those figures? Yeah. So your second question was?
I think that was the main question in that one. Any other? We have one more coming your way.
Thanks, Shamsuddin. Great notebook and tutorial. I was wondering if you could just comment on kind of the minimum size of lakes for getting a time series. It seems like the observation plan of ICESat-2 may miss some smaller lakes. I know one group is doing a project and they didn't really have any intersections of tracks with a smaller mountain lake. So in your experience, have you come across that? And what do you think the kind of minimum size is to get repeat measurements?
Yeah, so yeah, thank you for the question. So now looking at ICESat-2 itself, ICESat-2 has a resolution of 17 meters. And where I've experienced this is more in the Arctic. So in the Arctic, we have very smaller lakes. Lakes that are around, let's say, 0.007 kilometers square, which is around less than 100 meters. So from my current research, I was able to identify ICESat. But when the major problem with the ICESat monitoring those smaller lakes is that you don't have observation always. So you might, we know like ICESat is the temporal resolution is 90 days. And when your lake is bigger enough, you can get more shots in less than 90 days. So the problem with the smaller lakes is that they are not able to get those observations frequently. So between 2018 and 2019, and 2023, you can just get maybe like 4 shots within that particular lake. So lake as small as 100 meters, or let's say 50 meters, do not get shots in this particular this satellite. And another thing is that because ATL13 is based on, let's say, a database, I've forgotten the name of the database, but the database comprises of different lakes in different regions. So they looked at more bigger lakes, maybe like from 100 meters upward. So they did not look at like the smaller lakes. So in place of ATL13, you can decide to use, let's say, ATL6, or you can even decide to use ATL3, because ATL3 has all of the data that you need. So the least I can say ICESat-2 ATL13 has been able to observe is 100 meters lakes, like lakes with 100 meters area.
Yeah, that's really helpful. Any other questions?
I'm sorry, just to add, currently I'm working on a particular project where we're looking at different altimetry. So we are using the spatial resolution for ICESat to calibrate Sentinel-3. So just to get a higher temporal resolution. So you can use that to calibrate. So probably when that is out, then you can take a look at how we did that.
That's great. That looks like that's in the paper that you've got listed there at the bottom. Is that right?
Yes, yes, yes.
Excellent. All right. Anything else? Any other questions? Well, Shamsuddin, thank you very much for joining us today. And we hope to stay connected with you in the future. Hope you have a good rest of your day.
All right. Thank you all.